Okay, hello and welcome to GEOG-1026, Visualizing Our Future, J-Term 2021. So the first week we're going to be focusing on accessibility and agency. And so I know that might kind of sound like we're just doing a transportation lab and it's all just transportation, which is true, but I would like us to start thinking of accessibility as an interplay between habitation and amenities. And so habitation is kind of, where do people live? Where do they work? And amenities are what do people want? And what are they trying to get? So the accessibility is kind of the interplay between those two concepts. And agency is when we throw in a social dynamic and we ask ourselves, okay, so there's this question of literal accessibility. How can people get to and from things? But then, is that accessibility equally available to all members of society? And so agency has to do with the ability for different people to partake in kind of that network. So our region of interest is New England, but for our first tutorial, our kind of study area is going to be one of the more urban places in New England. We're looking at Somerville and Cambridge. And these two towns are interesting because they are separate towns, but they represent kind of a unique single functional region. And I'm sure the people who live here would love to tell us how different they are. But they're often affectionately or otherwise known as Camberville. So we know there's a lot of interplay between these two towns, and they do often work together on planning initiatives. But we're going to be doing a hypothetical project where we're imagining that these two towns want to do an open space network analysis so they can see how their open space is available for their residents. So the question is, what is an open space network analysis? And the basic idea is that you should be able to walk to some form of open space and have a diversity of options for where you can walk to for open space in your residential neighborhood. And there's been a bunch of literature lately about this in the past 10, 15, 20 years. One of the better known ones about kind of developing walkable cities is by Jeff Speck, a good read. There's also, if you want to just get the short and sweet YouTube video version of it, he did a TED Talk, which I'm sure at this point is a little dated, but the idea hinges around this ped shed or this pedestrian shed, and you've probably seen these before. They're walkability maps. How far away, how much time or how much distance along a network is it to get from one place to another. And so in planning, these ped sheds have traditionally just been done with circles, which you might think, okay, well, I learned in GIS that a cost distance or network distance means that if I want to walk, for 5 minutes, it's not going to be a perfect circle where I can get to, right? So this is a Euclidean kind of object, whereas we're going to be dealing with mostly network objects. And I've heard some arguments that, well, street networks can change, and so functionally the circle is still a useful tool. But if we want to do what we're going to be doing, which is an existing conditions kind of analysis for Friday, we want to know what are things like now, not what could they be, but what are they like now. And so to do that, we're going to be making what are called isochrones, and you probably know what they are more, kind of just intuitively. But an isochrone it's from the Greek iso, meaning same, and chrone, meaning time. And so the isochrone is kind of this contours of time. How many minutes or how many miles or feet or whatever unit of measurement is the same from a starting point. And so the open space network is what is the network of open spaces in these communities so that within a certain distance from those places, let's say a 10-minute walk, how many places are within a 10-minute walk? Not just, okay, yep, let's do a 10-minute walk from everywhere. There's a certain level of coverage. Maybe there's a few little deserts, but we want to see the redundancy, right? If we're here on Beacon Street, perhaps we have 2 options within a 10-minute walk. Or perhaps if we're here, we have 3 or 4 options. So the two towns would like to see what are the diversity of options. And I've worked in Somerville and Cambridge a few times. I haven't done this analysis specifically for these communities. I did do an analysis like this for a different community. So even though this is hypothetical, it is based on something that I've done for a client. Okay, so let's actually look at an isochrone just to see kind of some of the dynamics of it. We can kind of get into what they really are functionally. So this is a great website. You can do a certain number of free isochrones and other types of routing services every day. It's based on the OpenStreetMap database, and it's called Open Route Service. So you can do routing. There's a whole bunch of things you can do there. We're mostly just working with isochrones, so I'm on that right now. The cool thing is that they build in different modes of travel, but we're going to be specifically thinking about pedestrians for this one. So I'm going to choose pedestrian. You can even do hiking, so there's topography, but we'll just do walking. And isochrone options. So what we got to do is pick a spot. Let's go to Porter Square, which is kind of right on the seam between these two communities. And so what I might do is I'm going to just type in Porter Square. And nope, not the United Kingdom. There we go, North Cambridge. So it created an automatic blob here for us. And what are we looking at here? We're looking at, allegedly, they're telling us this is a 30-minute walk from Porter Square, and they're 15-minute intervals, right? And so kind of the cool thing about this is that you can kind of change the settings. This is based on time instead of distance. So yeah, it's kind of fun to experiment around with this, but what I want us to think about is what's being represented here, right? And I know you might just be thinking, oh, well, we're looking at an isochrone. That's what we've been talking about. But when I say what are we looking at, we're really looking at just a geometric object that an algorithm spit out, right? And so we have to kind of think about what is the algorithm doing and what are the inputs and outputs, because depending on what algorithm we choose, we want to be able to have confidence in our deliverables. So the reality of this object is that the algorithm is taking a starting point. It's following along a network and creating some kind of calculation in which there are nodes and edges or vertices and lines that kind of tell us in this network how far things are and how much time or distance it takes to get there. And so in 15 minutes, it might have on every single node in that network a value that says, yes, here we're at 15, here we're at 15.1, here we're at 30. But so then how does the algorithm decide what to do in this situation? So let's say there's a 15-minute point here, and a 30-minute point here, and a 30-minute point here, and a 30-minute point here, and probably one there, and one there. But how does the algorithm decide to draw these kind of intermediary points where it's just saying, okay, well, a little bit more, maybe it's these houses, but a lot of these points are kind of right in the middle of nowhere. And so what are those geometric objects, right? We go down here and we see, well, it makes sense. You can cross the bridge, so there's a little bit more access there, and there's less access here. But then this blob kind of goes completely over the river where there's no bridge at all. And so it's telling us that this is within a 30-minute walk when we know that is almost certainly not true. What we're looking at geometrically is called a minimum bounding geometry. And a minimum bounding geometry could be any number of shapes, right? One you might have seen before is a minimum bounding circle, and there's kind of a whole branch of mathematics it's really interesting. But a minimum bounding circle would just say, okay, here are a bunch of points. What is the smallest circle that can kind of make sure that all those points are inscribed within it, right? So if our algorithm for our PEDCHED analysis used a minimum bounding circle, it would almost certainly include locations that we would know are actually further away than 15 minutes, but it would be a very computationally kind of quick and simple way to do it. And that's kind of what this is, right? This is a minimum bounding circle around places we know that are 400 meters away from the source. So we're trying to move away from the minimum bounding circle as our minimum bounding geometry to represent an isochrone because we know it's pretty inaccurate, and it overestimates in general what the actual walk shed is or ped shed. Another one is, I mean, there's minimum bounding boxes, there's minimum bounding, a bunch of different things like that. There's a convex hull, which is a little better, and the convex hull is a minimum bounding geometry that kind of draws lines from the outermost points or vertices in any given kind of point cloud or vertex cloud. And so a convex hull is a little bit better, and I'm going to show you how to do that when we get into Q. And then, but what we're really looking at is kind of this concave hull. And a concave hull is different than a convex hull because a concave hull makes decisions about when to kind of tighten up this object and kind of create a little bit more nuance about what is included and excluded in this area. And so these concave hulls with street networks can get pretty complicated, right? As we looked at here, there's often decisions about, okay, well, how is there a bridge there? No bridge there. This is an error. This should be trimmed probably to the river, right? But there's not really a computationally easy way to do that. And so sometimes the concave hulls can get kind of messy. And we'll look at that when we move to Q in a couple minutes here. So instead of trying to get into the weeds about what kind of concave hull and how the different algorithms choose those, I don't think that's really going to be useful for us today. What I want to do is just to show you how to make convex hulls, this simple, very kind of computationally simple and conceptually simple way of drawing the most basic line from outer point to outer point in these kind of obtuse angles. And then we're going to learn about a couple different services that you can use in Q to create a myriad of these objects. So the next thing I'd like to do before we move on to the next video is go explore our data in Q and see what we're working with. So in the next video, I'll go over more about start creating a Q project file and kind of the data management side of things. But for now, I just want to talk about a couple of definitions that might be tricky. What we've got here is a road centerlines file, and it might seem very self-explanatory, but as cartographers, we get used to thinking of roads as just like a single line feature, but they're really complex objects, and working with planners has helped me to realize kind of that I need to revise my own concept of what a road is. So let's just look at a couple of examples, right? It might be easy to look at this centerlines file and just think, well, it's a center line. It represents the center of the road. But that's only really true if the road is simple, right? If it's a road in the countryside or something, then yeah, it might be the dotted line. It's just a center line. For more complex areas, though, we might have multiple directions in which it's either two roads going two separate ways, or maybe it's one kind of avenue with two directions, but they're kind of functionally separate in terms of where the cars can go. And so the center line, for instance, at a regional scale may just be in this median, even though no cars can go there. It just represents the avenue as a whole, or the boulevard as a whole. Or it may represent kind of these individual roads within that avenue, and the center line might be right kind of between these, or wherever the center of that pavement is, So there'd be two center lines. Or if it was a hyper-local analysis, maybe there'd be a center line for each lane. So it'd be kind of like lane center lines. So for this class, and this is where I'm probably going to butcher it and get in trouble a little bit, I want to regularize our terms for describing roadways and transportation. This entire area in terms of property law is called a right-of-way. So the entire space that is public that we're allowed to use, everybody can use is a right-of-way. We're going to call the thoroughfare kind of this next boundary in. The thoroughfare is anywhere that there is motion happening, and it can be multimodal. It could be pedestrian, It could be bike lanes, that kind of thing. So the thoroughfare is really this kind of this big object of like the principal land use, the purpose of it is motion. Edge of pavement, excuse me, edge of pavement is any contiguous area that is asphalt, right? And so a lot of planners have edge of pavement files, and that helps kind of create base maps that look, they look kind of visually consistent. And the edge of pavement could include kind of a roadway or a bike lane, and often it can include, parking spaces or, crosswalks and things like that. So we've got right-of-way, thoroughfare, edge of pavement, and then I want us to call any contiguous, let's just say linearly contiguous asphalt to be considered a road, right? So somebody might call this whole thing a road, right? We're going to be calling contiguous places that cars can go, regardless of direction. If these two cars were going in different directions, but they shared the same contiguous space, we're going to call it a road. A lane is the smallest unit, and that's the width of a car plus a bit, right? That's kind of functionally just where one car would be at any time. So we've got lane, road, edge of pavement, thoroughfare, and right-of-way. So it's not perfect, but that's what we'll do for this one. And there are many, many other terms which we can discuss. Like a bike lane is part of the edge of pavement, but it's not, in my book, part of the road right now, right? So anyway, that's what we're going to do there. I want to look also at buildings, because it seems like a building should just be a building. But let's pull in that file. Okay, and let's pull in that image as well. So a building footprint should, in theory, represent the physical space that the building occupies on the ground. The problem is that it's often much easier to digitize the roof print of a building, right? So this is a pretty good example right here. What we're seeing, that's a 2 meter. Get the 1 meter in there. There's a building, right? And the building footprint is really the roof print. What we're seeing is, it was much easier to digitize the roof, and almost all of these large buildings, the roof is extremely similar to the footprint. So it's kind of, we're assuming the geometric shape is the same, but there's obviously some error. The most common error is this kind of roof print footprint problem. So we know that if we trust this NEIP image to be pretty darn close to the truth, then the actual footprint of the building is to the to the west. Sometimes this will get corrected for, and it usually is in cities with skyscrapers. Let's see if we can find a good example over here. And it seems like, here's a good example. Here's a building in which we know that when this image was taken, whatever is not directly underneath the camera or remote sensor, which is called the nadir, anything away from that is going to kind of bend away. And so here is a building where the footprint has been corrected, so to speak. So the footprint really does represent much closer to where the building footprint is than if they had just left it as a roof print. So the taller the building, the worse it's going to be, and the further away from the center of the image, the worse it's going to be. In this case, I think it's probably several hundred feet or more where it's incorrect there, but they've corrected it. So another thing that can happen, you can see that there's all these smaller polygons, and they're trying to represent the kind of multiplicity of objects on the ground. A lot of times courtyards or things like that will be not accounted for. So the building footprint file is very useful. It's the most common thing we use for representing built space in a vector way. But these files are always fraught with different types of problems. And, if you're working with an urban designer, they're almost always going to be creating from architectural, in CAD, from architectural drawings, the actual site plan. So even though these building footprints are inaccurate in different ways, it's still useful at the neighborhood scale because they do a pretty darn good job of showing us where there are buildings. So anyway, a building isn't a building and a road isn't a road, but they they both are, those are the functional terms that we need to be careful about. All right, on to the actual meat of the tutorial. Thanks for sticking with me. I know this was a long one.